Well, before we proceed any further, let's do a couple of things. First of all, let's just save what we have so far in the project. So if we come to save, and let's call it Funes Borneo 1. And it will be saved in this format. It's just an ASCII file, so let's take a look at it. So this is the file, and this is what it contains. So here we have the time series, where they're read from, which column they should read, what is the node data value, what's the internal name that it will use. Then we have the parameters for each of the time series now, and later we will talk about this, what it means, this weight or inverse and volumetric. So here we say which one is the dependent, so the inflow is the dependent. And these are actually parameters for the Funes model. We have already seen the threshold. I talk a little about the gap, and we talk about extrapolation. Here actually are these three values here. So we will refer later to this file. And one thing is that an advanced user could easily come here and change things directly in this file instead of using the interface. So that gives them more flexibility to work with the model. The other thing I wanted to show you is that we have these correlation graphs that we can use to see better than just looking at these numbers here. So we can see how our observed data and our model data, how do they match. If they would match perfectly, obviously all these points will be in a 45 degrees line. So we can see that the model it gets the general idea of what's going on, but it doesn't really work very well. So what can we do? Well, one of the things that we could do is first is try to give different weights of different variables. But how would I decide which weights to give to each? Well, we have this tool that allows us to calculate the correlation between the dependent variable and the independent variable. So if I select this first precipitation time series, I can click here and see the correlation with the dependent variable, with the inflow. So as we can see, there's not a very good correlation, so 0.5 in this case. Let's see what happened with the second one, and if I say show, this one is even worse, and this one show correlation, this is kind of intermediate, 0.4, and finally this one show correlation with dependent. And well, here we see that none of the precipitation are strongly correlated to the inflow. And that's one of the beauties, I think, about this Funes approach, because even though we don't have good correlation, good obvious correlation, we can still find some kind of good correlation in the results of the model, and this will become even more evident in the future. So, well, I was mentioning that we could use that as an indication of what weight to give to different parameters. In this case, they all seem to be pretty similar, so it doesn't really matter which of the which weight. They all should have probably the same weight. But there's other things that we could do. For instance, one of the problems we find in hydrology is that the behavior of the watershed depends strongly on the soil moisture. And we don't have any data about soil moisture. And even if we had, it's likely that we won't have any forecast data for the soil moisture. So we can't really use it here because we wouldn't know what to put here. So in one of the projects that we did using Funes, we explore this option that works really fine. So we know that the soil moisture is related to the precipitation in the previous days. So if we can analyze the correlation between the one independent variable and one dependent variable, but we aggregate it a different number of days, so this will will aggregate the correlation, aggregate the precipitation 1 day, then 2 days, and 3 days, and so on. So FUNES can easily perform this analysis for us, and this is what we get. So with this time series Nanga Tuton, we can see that we start with this initial correlation, so this is 1 day, and then as we keep on adding more days, we see that the correlation becomes stronger and then it goes down again. So about 14 days is when we have the high correlation. So this would be an indication that probably the precipitation of the last 14 days is also related to our inflow into the dam. So let's try another one. So let's see, Batangay Dam, show aggregated correlation. And again, the peak of the correlation, it's about 14 days. So this is a kind of a good indication of what we should be doing. Another thing that we could try is to see, in hydrology, another very important concept is the time of concentration. So how do we account with that? So we could have probably a very strong precipitation, but that won't reflect in the inflow the same day, depending on the size of the watershed. So we also provide this other tool that calculates the correlation, but after shifting the time series back and forth. So if we see, for instance, in this case, in Batangay Dam, we see that for some reason it's much more correlated to the previous, from the precipitation to the previous day than from the following days. Right? In this case, it doesn't really make sense. We wouldn't, this part of the graph is not relevant because we wouldn't, let me see, no, this part, because we wouldn't correlate the inflow to the precipitation in the following days, right? But just to show that we have the possibility to compare the shifted correlation. So with all of this information, we can now start processing data and creating new time series. For instance, one thing that I would try immediately is to create this aggregated time series using 14 days to aggregate the data and then incorporate them into the model and see what effect those have. So we're going to see a little of those in the next videos.